In today's lesson, we're going to continue our investigation of continuous random variables. And in particular, we're going to start looking at some famous continuous distributions. So in today's lesson, we'll look at the normal distribution. In the next lesson, we'll look at a few more different continuous distributions. And after we've done that, we'll sort of be at the end of our pure probability section. And then we'll move back into using all of this probability knowledge that we've acquired to start doing some statistics. And so today's lesson is introducing the normal distribution. This is definitely the most important distribution in all of probability and statistics. It comes up all over the place. And so we'll sort of try to emphasize why it's an important distribution, but you're going to become quite familiar with it throughout the remainder of the course. So in today's lesson, we're wanting to understand what the normal distribution is, its use cases, the structure, the general image you should have. We also want to understand the standard normal distribution and how we are going to make transformations to or from the standard normal. We will look at something known as the empirical rule, which is sort of a quick way to do some calculations using the normal distribution. And we also want to understand how we can use the normal distribution to approximate other probability distributions. So we're going to be introducing quite a lot of use cases for the normal distribution in this lesson, and those use cases are not going to stop after the end of this lesson. We're going to keep using the normal distribution more and more throughout the remainder of the course. So to begin, I'm going to include a fairly outdated meme here, which is certainly not funny to anyone who's not already sort of in statistics, but if you've dealt with statistics enough, it might be enough to make you smile. And really, I think the key point that I want to emphasize here is that when you start to learn statistics, the normal distribution becomes assumed everywhere. We start using it in all sorts of different places. We assume that data are going to be approximately normally distributed. Everything sort of starts to follow around the normal distribution. And there's some good reasons for this. It does actually come up naturally in many places, and there's some sort of mathematical reasons why it's going to come up in other places. But it's also just really easy to work with, comparatively speaking. And so a lot of procedures are built assuming that data are normally distributed. And a lot of what we're going to see for the rest of the course as we begin to introduce some of these statistical ideas are going to assume normality. And this is great. This is a good way of introducing these statistical ideas. But I think that it's important to remember that while the normal distribution is a great theoretical tool, while it's going to be very applicable in many, many scenarios, it's not the be-all and end-all of statistics. You're going to end up with data throughout your work in the real world, which does not follow a normal distribution and which cannot be approximated well by a normal distribution. And so I think it's helpful to think about the normal distribution as almost being an illustrative example, one which is easy to work with, one which is nice, one which behaves well, but ultimately one that's not going to be the only applicable distribution, right? So instead of when you get your data, yelling at it because it's not normally distributed, perhaps take the ideas that you first looked at with the normal distribution and see how you can broaden them to data which are not normally distributed. So as I mentioned, the normal distribution is the most important distribution, all of statistics and probability. And when we're thinking of the normal distribution, we're thinking of this sort of standard bell curve shape. So if you've heard someone talking about a bell curve, they're probably talking about a normal distribution. And the reason it's called a bell curve is because when you plot it out, it sort of looks like an old bell. Many natural phenomena are going to be characterized well by the normal distribution. So we could think about heights, weights, measurement errors when you're measuring something in the real world, human reaction times. Oftentimes the grades in a course could end up being normally distributed. A whole lot is going to follow these natural bell curve shapes where most people fall sort of in the middle, and then you can sort of have these extreme tails. The distribution is going to be symmetric. As I mentioned, it's a bell-shaped curve, and we use two parameters to characterize it. So we have the mean, which we denote by mu, and this is the expected value. This is the population mean. We also use the variance, which we denote with this sigma squared, character here. Some people may use the standard deviation, the square root of the variance. I'm going to try to use the variance throughout, just as the canonical parameter of it. And I think that's slightly more common in statistics. And so with our mean and our variance, and these are the population levels, then we've defined sort of uniquely this curve. Again, using the standard deviation will be equivalent. If you're ever given the standard deviation, you just square it to get back to your variance. We have an explicit form for the density, right? So this is a density that will probably come up quite often, and so it's worth at least feeling somewhat familiar with. So we have this constant term out front, which is given by 1 over the square root of 2 pi times by the standard deviation. Right? And that's sort of a scaling term. That's going to be the term that makes it so that this whole thing integrates to 1. And then the bulk of the distribution is given by this exponential term. So it's e to the power of the negative, and then you take x minus mu, so the distance from the mean, squared, scale that by 2 times the variance. Okay? And so that's the density here. X can take any value between negative infinity and positive infinity. And you could use this density here, you could integrate it to show that the mean has to be mu and that the variance has to be sigma squared. We also have that this is going to be a valid density, by which I mean it's always positive, which isn't too challenging to see, and also that it integrates to be 1. It's important to note that there's not going to be a closed form solution for the CDF. We can calculate values for the CDF by integrating this expression, and there's lots of ways to approximate it. There's lots of software out there that will do that for you. There's tables that you can look up with all of these values, but we don't have a closed form way of writing down what the CDF of the normal distribution is. We can look at sort of graphical representations of the normal distribution. And so here I have 4 different normals plotted. The blue one comes up highest in the center there is mean of 0 and then a variance of 0.2. And so we can see the variance is kind of small, so the bell curve is kind of squished in, right? If we go over to the green one, which is the one with the peak over on the left side of the screen, that's going to have a mean of -2 and a slightly higher variance of 0.5, right? So it's a little bit more spread out than the blue one is. The red and the yellow, the other two that are centered on the middle of the screen, are both mean 0, right? So they're centered in the same place that the first one was, but we're increasing the variance more and more. And so the red has a variance of 1, and you can see it's more spread out than the first one we looked at, and then the yellow has a variance of 5, so it's even more spread out. So as the variance increases, we're flattening the curve. And as we lower the variance, we're narrowing the curve. As we change the mean, we're moving around where that bell curve is actually located. The form of the PDF can make probability calculations challenging, as it's an integral which can be hard to solve analytically. Normally, what we're going to do is use software, for instance, Minitab, or looking up normal distribution tables in order to actually solve for the probabilities of this. Now, one common strategy for doing this is to convert to what's called the standard normal distribution. The standard normal distribution is the normal distribution with a mean of 0 and a variance of 1. And anytime you have a normally distributed variable that you know the mean of and you know the variance of, you can scale these so that they have mean 0 and variance 1. In order to do that, if we say that x is going to have a mean of mu and a variance of sigma squared, then we can define this new random variable z, which is x minus mu divided by the standard deviation, right? And if you do that, you can work out that it's going to have to follow a normal distribution with mean 0 and variance 1. And you should be able to figure out the mean and the variance just using our properties of expectation and variance that we already know. The fact that it still follows a normal distribution is quite convenient. And so the idea is that anytime you're given a normally distributed random variable, if you know what its mean and variance are, you can rescale it and center it so that it follows this normal 0, 1. And then the values for the normal 0, 1 have been calculated many times over by all sorts of different sources. And so you can sort of look up what are the values on the normal 0, 1. And that's a common way of computing probabilistic values here. When we're dealing with the standard normal, we would denote the PDF with this lowercase phi character here, and the CDF is going to be with this uppercase phi character here. And generally speaking, we're going to use the letter Z to represent a standard normal, right? So we'll have X as whatever the random variable is that we care about. And when we normalize and scale X, we're going to get to the standard normal, and we'll call that variable Z. Doesn't have to be, but that's just the convention. Now, we can undo this transformation. So if you have a standard normal and you multiply by the standard deviation and add a mean, then you can convert back to the normal mu sigma squared, right? And so you can go both ways. And so it becomes helpful to be able to make a statement about the standard normal and then convert that statement back to whichever normal we care about, or vice versa. Now, some properties of the standard normal. Almost all of the density falls between plus and minus 3. So more than 99% of the values on the standard normal will fall between -3 and +3. And we can sort of do that conversion and see that the same is going to be true, except plus minus 3 times the standard deviation away from the mean, right, in general. But almost everything's going to fall within plus and minus 3. We can look up all of the values for the standard normal. So we can look up the CDF values, right? And it's basically just going to be a table that tells you if you plug in Z equals whatever, this is the corresponding probability here. Now, I'll show you these tables in class. You'll get a chance to look at them, but I'm never going to expect you to use them in this course. In my opinion, these tables are a very outdated way of computing normal probabilities. They'll be all over intro stats courses. You might require them in other statistics courses in the future, and so I'll show you them. But in this class, we're going to rely on software to compute it, because all of these functions have been programmed well into software, and if ever you need them on a closed book exam, then you'll just be provided with the critical values that you would need there. Now, the percentiles of the normal distribution can be found the same way that we saw computing the percentiles of any distribution, but we were going to care a lot about these percentiles. All right, so we'll actually just define ZP typically to be the pth percentile of Z, and then we can convert this using that conversion formula we saw to be the pth percentile for X, right? By taking mu, adding the Z, the pth percentile of Z times by the standard deviation, right? So we can do that conversion there. So again, because people have computed all of these values for the standard normal, we can get them for any normal distribution just by doing this conversion here. Now, oftentimes, instead of thinking about them explicitly as percentiles, we will think about them as what are known as critical values, okay? And the basic reason is that as we move through into the rest of the statistics course, we're mostly going to care about values that are in the tails of the normal distribution. We're going to care about high values and we're going to care about low values. And everything else in the middle is not going to be so much interest to us. And so if we take that pth percentile, Z alpha in this case, for instance, the alpha percentile, then we will typically refer to this not as the alpha percentile, but instead as the alpha level critical value. So if we're talking about the critical value at the 0.05 or at the 5%, then that's going to be the value such that 5% of the distribution falls below it. Right? We'll often be concerned with the fifth or the 95th, as well as the 0.25 or 0.025 and then 0.975. And these are going to be the values that come up most frequently, but other critical values will exist as well. And you'll get very familiar with what are these actual values. You'll get used to plugging them in calculations, all of that type of stuff. Now, because of symmetry, we'll actually be able to say that if you have Z alpha, then if you wanted to find 1 minus alpha, it's going to be the negative value of that, right? So this just follows from symmetry. We know that the normal distribution and the standard normal is symmetric around 0. And so if you want to have, say, 5% below the distribution, then you can go to, let's put 5% above the distribution, and it's going to be the negative corresponding value. Now, all of this can sort of be represented a little bit more concisely with what we'll call the empirical rule. And the empirical rule gives us a quick way to determine what we would expect to see on the normal distribution, and it's related to that statement about most of the value falling between plus and minus 3. So essentially what we can say is that around 68% of the observations with a normal distribution are going to fall within one standard deviation of the mean, right? So it's actually about 68.27, but if you take the mean plus or minus one standard deviation, about 68% of our observations are going to fall there. About 95% are going to fall within two standard deviations of the mean. So from mu minus 2 sigma to mu plus 2 sigma, 95%. And then 99.7% of values will be within 3 standard deviations of the mean. So again, almost everything is going to be within 3 standard deviations of the mean. This is where we get over 99% of the values fall within plus or minus 3 on the standard normal, right? And so this rule is going to be very helpful to remember. It's going to allow you to say, are things reasonable? It will give you a quick way to determine some very brief calculations, right? That 95% at plus or minus 2, that's often going to end up being used to do some quick calculations for what we are expecting to see. Now, we can also use the normal distribution to approximate other distributions, and because of how central the normal distribution is to statistics and probability broadly, this type of approximation is going to be very commonly used. So the most commonly used one for us is going to be the normal approximation to the binomial. So if we take n to be large and p to be around 0.5, then we can just approximate the binomial distribution by a normal distribution. Now, we can sort of write down what the mean and the variance of the binomial are, right? We know that the mean is going to be NP and the variance is NP 1 minus P. And it turns out that when you're approximating, you just set those two values equal, right? So you take the normal to have a mean given by the mean of the binomial, the normal to have a variance given by the variance of the binomial. And in terms of notation, when we write this tilde with a dot above it, we're saying that it's approximately distributed in that way. Now, normally we're going to say that this works well as long as both n times p and n times 1 minus p are larger than 10. Again, as with all rules in statistics, this is helpful guidance, but it's not sort of a strict rule. There might be times where you can get away with using it if these thresholds aren't met. There might be times where these thresholds are not going to be sufficient for you. And so it is sort of up to the situation. But as a general rule of thumb, if both of these are about 10, then you should be all right. Now, because the distribution is discrete, because the binomial is discrete, we need to use a continuity correction, right? So what do we mean by this? If we wish to solve for x less than or equal to some value x, then we really should consider the continuous case of x being less than x plus 0.5, right? And similarly, if we want to get larger than or equal to x, then we should consider cutting off the threshold by minus 0.5, right? And so why do we do this? Well, if you think about the binomial distribution, right? In terms of the binomial distribution, we're only able to have integer values, right? So we can only get 0, 1, 2, 3, and so on. Okay. Now, with our normal distribution, we can get any of the values in this range, right? So we're actually sort of dealing with a range here. And so if you think about if you observed a normal distribution, and let's say you observe it at 0.5, right? Well, we know that if you were to do this, and then you're saying, what's the nearest integer? Well, we're going to take this 0.5, and we're going to include it up to 1. And in fact, we're going to include everything up to 1.5 as corresponding to this 1, right? And so in terms of what's the probability that we are observing this 1, well, really, with our normal distribution, it's going to be anywhere between 0.5 and 1.5. And so if we have some threshold, right, and we want to say, what is the probability that we observe something less than or equal to k, right? And then we'd have k minus 1 here, and, k plus 1 here. Well, when we're dealing with this sort of normal distribution, if we had anything up to k plus 0.5, then we're going to call that k, right? And anything above that is no longer going to be k. So instead of using k as our threshold for the approximation, instead of saying the probability that our binomial is going to be less than or equal to k, well then what we're going to do instead is we're going to solve for the probability that our x variable, once we've normalized it, the normal distribution, is going to be less than or equal to k plus 0.5. Okay, and so here what we're thinking about is that this x is going to be a binomial, and that this x dot is going to be the normal approximation. All right, and so we're going to use this continuity correction. Now, one thing that I'll point out is it's important where the equality goes, right? So if we're saying x is greater than k, right? This is the same thing in the discrete case as x being greater than or equal to k plus or k minus 1, right? No, k plus 1, right? We can set the equality here. And so then what this is going to say is in order to be greater than or equal to k plus 1, then we want to be greater than or equal to k plus 1 minus 0.5, which is k plus 0.5, right? So this is how we would use it in the normal approximation. So it's important to look for where is the equality because we're dealing with a discrete distribution here. But generally speaking, we're going to do this sort of continuity correction there. This piece here about rounding down is exactly what I was just saying. My recommendation is if you're ever asked a question where you have to approximate the binomial with a normal distribution, set up your probabilities so that they have equalities in them, and then use the continuity correction as it's written on the slide here. Now, there's this question about why we need to use the normal distribution in the first place, and I'll walk through sort of the rationale, which is it's generally easier to reason about normal distributions, right? You're going to become very familiar with working with normal distributions. And so you're going to build up an intuition for working with what happens to normally distributed random variables. Now, because we have all of these normal tables computed, it's also generally easier to use this approximation, right? It's generally faster to do the calculations this way. However, with modern software, this is becoming less of an issue, right? It's no longer such a big issue because we can just plug all of these values in. And so because of this, the rule or the use of these normal approximations is becoming less relevant to us necessarily, but it's still important, mostly for that intuitive argument. The other piece is it gives us access to this empirical rule, which can be really handy, especially if you're just trying to have a quick understanding of what's going to happen. So, in summary, the normal distribution is an incredibly important distribution, probably the most important distribution. It's characterized by its mean and variance, and we have a closed form PDF. There's no closed form CDF. We'll often look at doing translations to the standard normal, which will help us with easier calculations and gives us access to the empirical rule. The normal distribution can also be used to approximate the binomial distribution, but we have to be mindful of that continuity correction. So in the next lecture, we're going to look at some more continuous distributions before moving away from probability and into statistics. So I hope to see you all in those lessons.